Hello everyone and welcome to another video. So today I want to talk about how to compute the length of a curve. So the idea here is you might have some curve drawn by, this blue line. Maybe let's call this curve C, and this might be described by some y is a function of x, right? So you have an independent variable x and you have a dependent variable y, and this function f basically provides a mapping which defines this blue curve, right? So the idea with the length of a curve computation is I would like to look at a section of this function between maybe some value, I don't know, right here, right? Between some independent variable x is equal to some lower limit a, maybe all the way up to some independent value of x is equal to b, right? And I would like to understand what is the length of the blue line between x equals a and x equals b. So for example, what we mean by that is, let's say you had this curve. I've got a little bit of wire here to try to approximate, well, I didn't do a super great job, but you get what I'm trying to go for, right? Let's say I take this curve, right, and it's like this, and now I want to get its length. I want to basically just stretch this thing out into a straight line and then measure this length from here to here, right? That would give me the length of the curve if it was flat, right? So the idea is, how are we going to go ahead and compute that given this framework, right? Well, I think everyone would probably agree one idea you could do is, okay, a first approximation is maybe let's take this range or this domain from A to B and let's chop it up into a bunch of sections. So maybe let's chop it up, here's one section here. The width of this section here is delta x, right? It's some delta x here. And then you might have another section over here. Maybe. Let's make it the same delta x. And I didn't draw this very convincingly, but the idea is you would have an equal number of delta x's, maybe you have 10, 20, 30, however many of these sections between A and B, and you're just going to carve this curve up, okay? And now what we're going to do is, okay, we still haven't gotten anywhere too much different because now I still need to compute the length of this little curve here. That's a little difficult, so the first thing I'm going to maybe try is, what if we look at a secant line that is straight between this section, right? So this is one approximation, is instead of computing the length of this curve here, I'll just compute the length of this red secant line, right? And I think everyone will agree that I can draw a little bit of a triangle here where you've got this length and this length, right? And I think everyone will agree that this is delta x, right? And this distance is a delta y, right? Nothing fascinating there. You got this right triangle at this point. So this red secant line, it's the hypotenuse of that. So I think everyone would agree that this length, right, is, let's call this, this length here h sub I for the hypotenuse of the ith element, right? For the ith chunk, okay? So I think everyone will agree from this is that the length of this hypotenuse, right, is just given by your Pythagorean theorem, right? So this length is just square root of x squared plus y squared, right? Now, what's interesting is, okay, we can now take an observation and say by the mean value theorem, what we know is that somewhere on this blue curve, there is going to be some point where its tangent to the curve is equal to the slope of the secant line, right? So in this picture, what I think it's probably somewhere around right here, right? At this point, if I draw a tangent line to this curve, right, it has the same slope as this secant, as this red secant line. So I'm just going to kind of draw it like this, right? So this magic point, it's some, I don't know where it is. Maybe let's just call this for now, it is x star, some unknown value, but the mean value theorem is going to guarantee that this point lives between this delta x range, right? Somewhere in this segment, because it's a continuous smooth curve, it's going to have to basically have one point at least which has this property, right? So what's interesting about this, right, is if I draw this accurately, it's basically, well, I'm having a hard time drawing this accurately, but you'll all agree that this slope here, right, this is given by what? It's the partial of the, sorry, not the partial, it's the derivative of the function with respect to x at this point x star, right? That's this slope, right? And I think everyone would agree that we could also get this slope by basically rise over run, because it's the same slope as this triangle, right? So you could kind of translate the triangle over if you wanted to, like this. That's probably the way to write it. Where you have delta x here, delta y. So this is equal to rise over run, or delta y over delta x, right? So again, that's what we've got right here, is that the mean value theorem is going to guarantee that there's some point x star where the slope of the function f is equal to the slope of the secant line. So again, we can write that the slope of the function at x star is equal to the slope of the secant line, which is delta y over delta x, right? Or it's just rise over run. So if I solve this here for delta y, right, basically just take the delta x, move it to the other side, we end up with this expression here, right? So delta y is basically the slope at that point times delta x. I'm just going to substitute this into the previous expression up here, right? So that's what I've got down here. Just plug it in for delta y, okay? And now you notice there's a delta x squared here, there's a delta x squared here. You can pull it then out of the square root, and we end up with this, right? So here, this is the length of this one little secant line right here, right? So that's perfect. That's just one little section. So I think what we can agree on then is if I want to get the approximate length of this entire curve C between the point A and B, right? All I'm going to have to do is I can approximate that length by basically just adding up all of these hypotenuses, these little mini hypotenuses, one at a time, right, over that domain. Okay, so notice I've got this length. This is the length of the total curve that I'm interested in between A and B. It's approximately equal to adding up all of these hypotenuses, right? So now what I'm going to do is do a little bit of calculus and say, okay, why don't I take the limit as this delta x, right? As this delta x gets smaller and smaller and smaller and approaches to 0, I think everyone will agree with the picture is you will get a lot more of these little chunks, but these chunks will get closer and closer to the actual function line, and you're going to get closer and closer to the actual length of the curve between A and B, right? So I can go from an approximate to an equal sign if I take the limit as delta x goes to 0 of this quantity, right? Just summing up all of these hypotenuses. And then as this delta x goes to 0, right, the other way we can write that, this is just a Riemann sum, and as I take the sum, the measure of that to go to 0, I basically just get the integral, right? So here's the expression for getting the distance of the curve, right? It's just the integral from A to B of this quantity square root of 1 plus, this is now the slope of the function f squared. So that's all you got to do. So it's a nice, easy, compact formula to get the length of that curve. So why don't we go ahead and apply this now to an example. All right, here's a kind of contrived example that I cooked up. So I basically took a circle of radius 3, I centered it at the location 2, 1. And now what I want to look at is I want to look at computing the length of this arc down here, which is part of this circle, as you can kind of see here. So I've calculated where A and B are. So A is this location here. I think this is about, well, in fact, exactly, it's 2 minus 3 over root 2. That corresponds to the point which is about, 45 degrees down on this circle here. So I'm going to start someplace weird, and I'm just going to now go all the way over here to this far point of the circle here. So this here is the B value of 5, okay? So again, what we can do is we can write the equation of this red curve that I'm interested in, right? So here it is, y is equal to some function of x, and again, here's the equation of the circle, and again, I've taken the minus sign down here to get the lower portion of the curve, right? Okay, so now what I would like to do is let's pick some numbers. So again, I picked these values, right? X naught of 2, Y naught of 1, and R of 3. So again, that gets me this picture here of this nice circle, radius 3, centered at 2, 1. And this is all set up, right? So now, sure, there are easier ways to compute this, but let's see if we can use our equation here, right? Which gives us the length of this arc, where all we need to do is compute this function's derivative with respect to the independent variable, square it, add 1, square root it, and then integrate from A to B. So again, just plugging in all of our expressions, the first thing we're going to need to do is compute the derivative of the function. So all I'm going to do is take the derivative of this thing right here, right? Here is the entire function. Take this derivative with respect to x, right? With respect to this independent variable here. And this is what you end up with, right? Go ahead and do it yourself. Go to Mathematica, whatever. This is what you end up with. So just take this, jam it into the equation. So that's all I've done here. This goes right down here. And again, remember this is inside the square term. I can't tell you how many people forget about this squared here. You need this squared bit, right? And then just go ahead, plug in all your numbers. So now I'm going to plug in x naught of 2, radius of 3, all that kind of good stuff. Plug in my a to b values. And again, go ahead and run over to Mathematica or some tool and just go ahead and calculate this integral. You end up with this, right? You end up with 9 pi over 4, okay? Now, again, you can go ahead and say, all right, for this particular case, there is another way we can kind of check our answer, right? We know that this is a circle of radius 3, right? So I know that the circumference of a circle is just 2 pi r, or it's just 6 pi in this case, right? Now, you got to remember, we don't want the entire circumference of this. I only want part of the circle, and I computed it nicely because it's actually, if you look at this, the fraction of the full 360 degrees that we care about, it's actually what? It's 360 minus 180, right? That gets rid of all of this stuff, the minus 180, and then minus another 45 degrees here. That gets me the part of the circle I still have. So I'll just take their circumference, multiply it by that amount, right? This fraction. And you know what? What's funny is you get the exact same answer, 9 pi over 4. So great, this works out well. And again, the beauty of this is you can use this expression when you have a much more complicated function. It works for pretty much any smooth, continuously differentiable function. So this shows how to go about using this length of a formula calculation. Let's get a little bit more complicated now. All right, so let's extend this idea now to a more complicated curve that's described by a three-dimensional parametric representation. So first off, you ought to make sure we understand what are parametric representations of curves. So if you haven't seen our previous video on this topic, please make sure you've watched that because we're going to use some of that idea in this discussion right now. So assuming you've seen all of that, what we're going to do now is, again, we're going to have ourselves a description of how x, y, and z components of a curve vary with respect to some independent parameter t, and we're going to use some parameterization as I've shown here with an r1, an r2, and r3, or you could describe this as a vector function as you see right here, right? So again, all this describes now is this curve C, which is now in three-dimensional space. So you've got an x, y, z. And again, it's the exact same thing as we saw earlier. So now you've got some curve floating around in three-dimensional space with some parameterization, and I want to now take this curve and stretch it and straighten it and then measure its length between 2 points A and B. Of course, now the A and B is the starting point of the independent variable parameterization t, and B is the ending point of that same independent variable parameterization. So again, it just goes ahead and describes some starting point and some ending point along this curve in three-dimensional space. So the idea is exactly what we did earlier. It's just a couple of small tweaks. So again, we're just going to go ahead and get the secant line, so to speak, between some small section here, right? And then we're going to get its length via Pythagorean theorem. So it's, again, it's just a delta x, delta y, delta z. The only thing here now is delta x, delta y, and delta z all change as a function of the independent variable t, right, the parameterization. So again, we do the exact same logic and say that by the mean value theorem, right, there is some point t star between that segment chunk, right, where the slope of the secant line is basically going to be the same as the derivative of the first parameterization describing x, its slope, its derivative with respect to t at that point t star, right? At that point, I don't know where it is, but mean value theorem guarantees it's going to exist, right? And then I do the same thing for delta y with respect to delta t and delta z with respect to delta t, right? I do the exact same thing. The only thing to maybe note here is that the point at which it matches is not necessarily the same for x, y, and z. That's why I've got a t star for x, t double star for y, t triple star for z, just to denote that, hey, the independent variable t value at which this is true might be different for the x, y, and z components, right? In the end, this is not going to matter, but we got to be careful here. Okay, so again, same thing. What we're going to do now is just go ahead and take this, and where did my black pen go? Oh, over here, sorry. Nope, that's not it. Oh, here. Okay, so what we're going to do is go ahead and just solve this for delta x, delta y, delta z, right? So that just means moving this delta t to the other side, right? So this is now times delta t. Same thing here, move this to the other side and get delta t. And then lastly for delta z, same thing, move it to the other side, delta z, delta t here. There, great. Okay, now just go ahead and substitute delta x, delta y, delta z into this expression here. That's what you get on this side, right? Okay, and again, we notice there's a t squared, t squared, t squared. Pull that out of the square root. And then notice here that this is basically the dot product, right? You can see this is R1, R2, R3, right? R1, R2, R3, and it's just the derivatives of each of those components. So I can rewrite this here as basically an inner product of the vector version of the parameterization R, right? And again, I've got this little denotation T tilde here because again, this is a little bit fishy because this is evaluated at T star, this is evaluated T double star, this is evaluated T triple star. So I'm going to use a little bit of hand wavy notation. This is going to not matter in about 2 steps, but to be completely correct, we have to have this. This is not a single value t, right? So this is a little bit odd right now, but let's leave it like this, okay? So again, you're taking the dot product now of the derivative of the vector value description of the parameterization, right? And then the other way sometimes you've seen this written in, which is a little bit cleaner, this is just the derivative of r. So let's just call this maybe r prime, okay? So now this is pretty nice. You've got one segment of this hypotenuse. This is just square root of the inner product of r prime, okay? Now, if we take the limit as delta t goes to 0, now suddenly this t star, t double star, t triple star, those all collapse to the same point, right? Because I'm taking delta t to become very small. So now is where I don't need this tilde notation any longer, and I can write the integral just like we did earlier. So we again come up with this very nice clean expression for the curve length between point A and B, right? It's just a square root of the inner product of r prime. And that's basically it, right? So again, very nice clean formula. Let's go ahead and maybe apply this to an example. All right, so let's revisit that partial circle example that we did earlier, and we're just going to use now our new formula for computing the arc length. So we see the first thing we need to do is get a parameterization of this curve. So we can get a parameterization easily for the entire kind of blue circle, right? We saw that was just a circle with radius r centered at x0 and y0. So I'm going to pick this parameterization, right? It's just r cosine theta plus x0. That gives me the x coordinates. T plus y, not theta. That gives me the y, and there's no z component to this parameterization because it's just in the xy plane, right? Okay, so with this parameterization in mind, we can obviously compute its derivative, r prime. Just take the derivative of this and this and this with respect to t. You get this guy, right? And now all I need to do in here is I just need to get a and b, right? So we know that given this parameterization, t of 0 is this point, right? And then as t starts increasing, it's basically an angle theta, right? So over here is where a starts and then keeps going all the way up here to b, right? So here's a and b, so I think you can compute that pretty easily. A is just, yeah, it's 180 degrees, and then we remember this is just another 45 degrees, and that's how far we go, right? So it's this part of 2 pi, right? That's the starting point A. B is obviously at t equals 2 pi all the way around. So at that point, we've got everything we need. Just plug it into our expression down here, right? And get this thing like this. So here it is. And if you go ahead and turn the crank, I think you're going to end up with 9 pi over 4. Exact same answer we got earlier. So that is perfect, right? Okay, one other thing that maybe I'll mention is that sometimes it's convenient now that we've got our good expression here that tells us the arc length between any point A and B. One thing that is sometimes helpful is instead I would like to know how the arc length varies as a function of the independent variable t, right? In other words, maybe the easiest thing to do is let's just start at a equals 0, okay? And then we're going to go up to an upper limit of t, okay? Of course, now what I need to do is let's change the variable of integration here so it doesn't conflict with the upper limit of integration. So let's change all these t's to taus. Okay, so that goes to tau, tau, d tau, right? Okay, great. So what this allows us now to do is basically compute the arc length going from the start of the curve up to some arbitrary limit of integration t, right? So let's just do that for our circular helix, right? And the nice thing about this is now instead of, well, I'll tell you what, let's just plug it in, right? Actually, putting that in, right, to that expression down there, just basically plug in r prime into here, and I skipped a few steps here. There's a dot, dot, dot that might need to go in here, but if you do all the math, you'll end up with this expression down here, right? So now what this does is it allows us to relate the independent variable of the parameterization t to the arc length. Or why don't we solve for t as a function of arc length? That's this down here, right? All I'm going to do is just solve this equation for t. And now what's nice about this is that it allows us to reparameterize the system instead of using this arbitrary variable t, which I guess, you know, in this parameterization t, you could think of it as it was the angle, right? It was kind of like this, right? It's at the angle as you move around this circular helix, right? But now we can resubstitute and reparameterize so that the independent variable is actually the arc length, or the length along the curve, right? So what I mean by that is, let's reparameterize this. Let's make another parameterization called r star, which is a function of s, right? And the way we're going to get this is we're just going to take the original parameterization here, but substitute in this relationship between how the independent variable t relates to s, right? So everywhere you see a t, just plug in s over square root of a squared plus c squared, right? So you just do that. Everywhere you see this t becomes this expression, like that, like that, like that, right? So great. What this now is, this is an alternate parameterization, right? So you can see very clearly see that r star is different than r, and they're going to tell us different pieces of information, right? They describe a similar curve, right? But just as the independent variable of t in this case, or s in this case, as it varies, you're going to get a different point along the curve, and those mean different things. So to better illustrate this, let's jump over to Mathematica and take a look at this. All right, so here we are. Let's look at two cases. So the first case I'd like to investigate is the original parameterization r, and we're going to let the independent variable t go between 0 and 2 pi. Now remember, this original parameterization, this independent variable t, what it physically corresponded to was sort of that angle, so to speak, around the z-axis, right? So this, if we let it go from 0 to 2 pi, this should generate one full, you know, quote-unquote spiral of this circular helix. And then the next case I'd like to look at is using the r star parameterization we just talked about. Now remember, now the independent variable in this case corresponds to the actual arc length. So I'm going to go from 0 up to, this is 2 pi times a. So this is basically, it's not enough length, so to speak, to generate one full spiral of the circular circle with a radius of a, right? Now, if c was 0, you know, that parameter c in our parameterization, if this circle was just in the plane, right, this should be the circumference of the entire circle, right? 2 pi times the radius, right? But because this helix is stretched out in the z dimension, we're going to see that this is not enough, you know, quote-unquote length to make it one full spiral, which is what we're kind of expecting. So again, let's go ahead and just choose some parameters. So for a radius of this spiral, let's choose 3. And for sort of the rate of growth in the z direction, let's choose c equals 2. So for the first case, with the original parameterization, right, that's what I'm plotting right here. You're going to see this parameterization. Let me scroll down a little bit, all right? This is what it looks like, right? It's a circular helix. Whoops, let me see if I can get this so it all fits on one screen, all right? It's an entirely circular helix, and it looks nice. And in fact, if we look at it from the top, it generates one full spiral. And in fact, let me come down here. I got a better picture of it. This is a top view, right? So we see that, yes, in this case, with this parameterization, t going from 0 to 2 pi, it gets you one full spiral. But again, this length of this spiral is greater than 2 pi times a. And in fact, that's what we're going to look at in the case 2. right? So case 2 is looking at r star, and I'm going to let this distance run from 0 to 2 pi a. And what we see in this case is you do not get a full spiral because the curve is just longer, right? So 2 pi times a is not enough to get you all the way around and complete one full revolution. And again, if you look at it from the top, that's exactly what you see here, right? So again, this is just an interesting alternate parameterization, because now the independent variable literally tells you how far or what the length of this curve is. So in this case, this curve length is 2 pi times a, which is not really the circumference of the flat circle, so to speak, right? So it's just a couple ways to look at this. So anyway, I think this is probably a great spot to leave it. I hope you enjoyed the video, and if so, I also hope you'll consider subscribing to the channel. We have new videos coming out every Monday, and we're going to continue this discussion on vector integral calculus with some other topics in the future, and I hope we'll catch you and we can all learn something new together then. In that case, I think I'm going to sign off. Talk to you later. Bye.